Okay, in the previous lecture video we have seen what is fragmentation and types of fragmentations. In this video we shall see what is paging, types of or uses of paging technique, as well as shared pages, and along with that we shall see segmentation. What do you mean by segmentation and difference between your paging and segmentation technique. First, now we shall see what you mean by paging. Paging is nothing but it is a memory management scheme that permits the physical address space of a process to be non-contiguous. That is nothing but it is a non-contiguous memory allocation. It avoids external fragmentation and the need for compassion. Next, it also allows the physical address space of a process to be non-contiguous. Here, logical memory is divided into equal sized pages and physical memory is divided into equal sized frames. As you can see here, this is your logical memory address space, which is divided into equal sized slot called as pages. So each and every slot or each and every partition is called as a page. And in your physical address space, if you see here, each and every slot is called as a frame. And each and every pages are stored inside your physical address memory. Next, as you can see here, page 0, it is stored in this position. Page 1 here, page 2, page 3 and page 4 respectively. But note that always the page size should be equal to frame size. What is it? How is it? We shall see next. Address translation scheme. What do you mean by this address translation scheme? As and when you are aware that CPU generates an address. Whenever CPU generates an address, the address is divided into two parts. One is your page number, another one is your offset value. Offset is nothing but displacement, which we have already dealt in your previous lecture video. So page number is nothing but it is an index to the page table which contains the base address of each page in physical memory. Next, page offset. What is this page offset? It is nothing but the displacement value. It is nothing but combined with this page offset value is always combined with base address to define the physical memory address. That is, you are going to add your offset value with the base address in order to fetch the address present inside the physical memory that is sent to the memory unit. So assume that L is nothing but logical address equal to page P D, that is page number D is nothing but displacement or offset within that particular page. What is this? We shall see using diagram. Here, as you can see, this is CPU. CPU has generated a logical address which is divided into page number and your offset value D. Now, whenever page number is generated, the page number will be searched inside the page table, and this page table will have the frame numbers where exactly that particular page is being stored. So after fetching the frame number, here if you see, page P is being searched inside the page table and F is the frame number. This F is being passed here and your displacement is being given here. After fetching the frame number, using with the help of your frame number and displacement, you are going to fetch your physical memory where exactly the page is being stored inside your physical memory. So next we shall see an example, that is paging model of logical and physical memory. Here, as you can see, this is nothing but your logical memory where it is divided into equal number of size and the pages are stored inside the logical memory. Your page table, what does it contain? It contains the page numbers and it contains the frame numbers. That is page 0, your 0. So page 0 is stored in frame number 1. This is the meaning. If you see your physical memory, check here. as you are aware, in the starting of the video we told logical memory contains the page numbers and your physical memory contains your frame numbers. So frame numbers are 0 to 7. So here page numbers are 0 to 3. So 4 pages are there and all these pages are stored inside your physical memory. So your page table, what it will do, it will give the mapping. It will tell where exactly each and every page is stored. For example, page 0 is stored in frame number 1. Next, if I see page 1, it is telling 4. If I go and check here frame number 4, page 1 is stored. Next, page 2. Page 2 is stored in frame number 3. 3, if you see here, page 2 is stored. Next, page number 3 is stored in 7. Frame number 7. If I check here, frame number 7 is being occupied with page 3. This is the help of your page table. It maps your page number and your frame number. It will tell where exactly the pages are stored inside your main memory or physical memory with the help of frame numbers. Next, we shall see what is this free frames. Always whenever a process arrives for execution, always the process is divided into pages. A process is divided into pages, that or it is expressed in terms of pages that is to be examined. Now here if you see a new process, assume process P1. So this process P1 is divided into 4 pages, that is page 0, page 1, page 2 and page 3. So all these pages should be placed inside your physical memory, So each page of the process needs one frame. Each page of the process needs one frame. Thus, if it has, or the process requires n pages, then at least n frames must be available in the memory. Now, how will I come to know which space is available? So with the help of this free frame list, I will come to know what are the frames available, that is free. So now if here in this example, if you see free frame list, it tells 14, 13, that is frame number 14, frame number 13, 18, 20, 15 are free. Others are occupied. So what I can do, this is the example of before allocating. And here if you see here, using this help of your frame list, I am trying to allocate the pages. So first page 0. From the frame list I can see frame number 14 is free. So frame number 14 will go and occupy with page 0. Next if I see here, if I see 14 is there. Next, page 1 is stored inside (13). Next, if I see page 2 with the help of this frame free list, it tells 18. So page 2 will go and sit in 18th frame. Next, it tells 20th frame is free. So page 3 will come and sit inside 20th frame. And now the new process page table. The page table of new process will be updated as shown. That is frame 0 with frame number 14 as you can see here. Next, page number 1, 13. Next, page number 2, 18. Page number 3, 20. Still I have one more free frame list, that is 15. It is as shown in your free frame list. And also when you are updating your page table, your frame list will also be updated. This is your diagram after allocating. The processes. That is nothing but your pages inside the processes. So this is the help of your free frame list. free frame list. Next, we shall see how to implement this page table, or what all does a page table contain. Page table is nothing but it is kept in main memory. It has two pointers in it. One is called as page table base register, which points to the page table, and one more is page table length register, which indicates the size of the page table, Now, in this scheme, every data or instruction access requires two memory accesses. Every instruction or data to be accessed, it requires two memory accesses. One for the page table and one for the data or instruction set. So this problem can be solved using a special type of lookup hardware called as translation allocation or translation look aside buffer. What is this TLB? We shall see. What is this TLB? We shall see. Now, as I told, CPU, it generates a logical address, it has page number, it has offset value. Whenever the page number is generated, if you recall your hardware part, directly you could have add your page table. No, so now in order to make the work fast, what we are going to do? We are going to take the help of this TLB. What is this TLB? Transition look aside buffer table. Inside this buffer table, we'll be having page number as well as frame number. What it will do, whenever the page number, that is logical address, is generated, the page number is first searched inside the TLB. Say suppose I am searching page number 1 and this particular page number is present inside frame number 2. So what happens? Frame number 2 is being given here, and your offset value will directly be coming here, and with the help of this offset value and frame number, you are going to fetch the data in the physical memory. So if in case whatever page number I am searching, page 1, is present inside this TLB, then it is called as TLB hit ratio. TLB hit. Say suppose I am searching for page number 2 or page number, I am searching for page number 21. First what happens, whenever the address is generated, it comes here, it checks here. But if I check here, 21 is not there. So what I'll do, I'll again come back, I'll check inside the page table. So somewhere here, I'll get page number 22. It tells that page number 22 is present inside frame number 4. So this frame number 4 is being fetched and it will be given to the next phase, and your displacement will be copied as it is, and 4 comma the displacement value, you will be getting your physical memory for that particular page 21. So when you are trying to search here and it is not present and then come and search inside the page table, then it is called as TLB miss. That is, the data whatever you are searching is not present inside the TLB. So if the data is present or the page number is present inside TLB, then it is called as table hit. If it is not present inside TLB, then it is called as table miss ratio or table miss, TLB miss. So now we shall see how to calculate the effective access time. That is, how much time is required in order to fetch or search a particular page number. Whenever I told you, whenever the page number is present inside the TLB, it is called as TLB hit. Whenever it is not present, it is called as TLB miss. So now if we see here, it tells that hit ratio, percentage of times that a page number is found in the associative registers, the ratio related to the number of associative registers. So how to calculate this effective access time? To calculate this effective access time, you can watch the video given in the below link, where I have explained taking an example how to calculate. That is nothing but your hit ratio into the number given plus number, that is number is nothing but the number of minutes taken to access a particular page, and plus your failure rate, that is your miss rate, plus the number of seconds taken to calculate that particular or fetch that particular page from the page table. So next, now we shall see how to give protection, memory protection. So why is your memory protection so much important? Why is the memory protection so much important? So memory protection in a paged environment is accomplished by protection bits. Protection bits, that is nothing but two bits, that is valid bit and invalid bit. And these protection bits are associated with each frame. It is associated with each frame. Normally these bits are kept in the page table. They are placed in page table. Next, one bit can define a page to be read, write or read only. I repeat, one bit can define a page to be read, write or read only. And at the same time that the physical address is being computed and the protection bits is attempt to write a read-only page causes a hardware trap to the operating system. If in case the position or the bit given is invalid and still I try to access that particular page, then it is called as a trap or error. So valid indicates that the process is there inside the logical address space, and invalid indicates that the process or page is not present inside the logical address space. What is this? We will see here. As you can see here, whenever the page is stored, the memory is from 0002 12 to 87. So here if you see page 0, it is stored inside frame, page 0, it is stored inside frame number 2 with the help of this. Next, so it is called as valid bit. Next, again page 1, 3, it is valid bit. If it is present, then it is valid bit, and you can tell that it is action can be read, write or read only. Read, write or read only. Next, if you see here page 2, that is also valid, page 3 is valid, page 4 is valid, page 5 is valid. But if I see page 6, it tells the frame number is 0. It is not at all present inside your physical memory and it is invalid. Invalid means that here if you see here, the program extends only to the address 104668. That is the logical address considered here is from 00 to 10,468, that's all. And any reference beyond this address is called as illegal. It is called as illegal access. Illegal access. That is why your page 6 is 0, invalid, and page 7 is invalid. So this is the help of, or this is the usage of your memory bits, that is valid and invalid, and it is always associated in your page table. In the next video we shall see what is shared pages, or what is shared pages, and what are the types of structures of page table.